So today what we're going to do is we're going to take a look at the limit laws, like I promised last time, right? So we saw limits by graphing and numerically, right? And then we saw continuity, and then we talked about how putting the continuity together with the limit laws, we're going to be able to evaluate limits algebraically. Okay, so today we're going to look at the limit laws and evaluating limits algebraically, and then we're going to do a lot of practice and a lot of examples. Deal? Deal. Okay. All right. So let's write them down. So assuming that suppose you have two functions and their limits exist. So then, let's see. So these are, we're not going to prove these. Because I don't think we'll gain much from the proofs for these, although we will prove a bunch of stuff, just not these. Okay, so let's say that you're finding the limit of the sum or difference of two functions. So what you can do is break this up into the limit of the first function and plus or minus the limit of the second function. Okay, and then you have the limit as x approaches a of f of x times g of x. So this is equal to the limit as x approaches a of f of x times the limit as x approaches a of g of x. Okay, now what if one of those two limits does not exist? What does that mean? Can you use the limit law? No. No. Okay, so remember at the very top there it says assuming those limit as x approaches a of f of x and g of x both exist, then you can use the limit laws. If they don't exist, one of them does not exist, then you cannot use them. All right. Perfect example of this. So let me do. So here, perfect segue here. Example. The limit as x approaches 0 of sine of x over x. Is this equal to the limit as x approaches 0 of sine of x times the limit as x approaches 0 of 1 over x? So sine over x is the same as sine of x times 1 over x, right? Okay. But what is the right side equal to there? If I evaluate each one of those limits, I can do that, right? Let's see here. What is that limit right there? Limit as x approaches 0 of sine of x. 0, right? Sine is continuous, so sine of 0 is just equal to 0. Okay. And what is this limit? The limit as x approaches 0 of 1 over x? Infinity. It doesn't exist, right? So it's infinity from one side, right? So like if you graph it, you can see. So it looks basically, the function 1 over x looks like this, right? So it's a very small graph. But so if you come in from the positive direction, it's going to positive infinity. Negative direction, it's going to negative infinity. So what do you say about the limit as x approaches 0? It doesn't exist, right? Well, you might argue that, 0 times anything is 0, so it's just 0, right? Is that a correct way of thinking? No, this is incorrect thinking. And the reason why is because this is not actually the number 0, it's approaching 0. And this, well, it's approaching does not exist, which doesn't even make sense. But even if you're approaching, say, okay, here is even better. Okay, let's just say hypothetically I go like this. I'm just going to change the problem here. I go like that. Okay, so now I'm just approaching from the right only. How does that change this right here? What is that now?
Positive infinity.
Positive infinity. Okay. So now it's even worse. What's 0 times infinity?
0.
So I hear 0. I hear doesn't exist. Who's going for infinity? Infinity times anything is infinity, right? Or 0 times anything is 0? Which one is it? Well, if you guys remember from looking at the graph, what actually is this limit? It's 1. Do you guys remember we graphed it last time? Well, how much sense does that make? No sense. That is right. Okay. So a couple things going on here. First is that limit laws do not apply. Why not? Why do the limit laws not apply in this case, in this example? Because one of the limits does not exist, right? Remember, infinity also does not exist. So the limit of sine does exist. The limit as x approaches 0 of sine does exist. But the limit as x approaches 0 of 1 over x does not exist. Yeah? So you cannot use the limit laws and break them up that way. Does that make sense? Were you going to ask another question? No? Okay. Now, do we now understand why this is equal to 1? The limit as x approaches 0 of sine of x over x. Why is that 1? The correct answer is no. And that's okay. That's okay. It is okay to not fully understand everything. Okay. Any questions?
Why is the sine of 0 equal to 0 again? Isn't it 1?
No, sine of 0 is 0. Right? So if you look at the unit circle, right, down here. Yeah, I think you're thinking of sine of, you're thinking of sine of x over x. So I'm just talking about just sine of x. Okay. All right. So let me erase this. So I wanted to put the third limit law here. Whoa.
And finally, this limit exists or doesn't?
It does. No, it does. It's equal to 1. But we don't know why. So, but that's okay. For now, it's okay. We will know why. We don't know enough yet. Okay, now the last one is that the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f of x divided by the limit as x approaches a of g of x. Now this has an extra wrinkle. As you can imagine, the limit as x approaches a of g of x cannot equal to 0. So even if it exists, if it equals to 0, then you can't use the loss. But that's obvious because you can't divide by 0. Okay, so all right, so let's put this to use. Are you guys ready? Yes?
Yes.
Whammo. Okay. All right, so this is our strategy. Strategy for evaluating limits. Okay, so first, if the limit is what is called indeterminate. Now, indeterminate is when you first try to evaluate a limit, remember if it's continuous, then the limit and the value of the function are the same, right? So that's the easiest way to evaluate a limit. So that's the very first thing you do to try to evaluate a limit. You plug in the number to see if you get a value out of it. If you do, then you're done. There's nothing else to do. But indeterminate is when you have stuff like, for example, if you get 0 divided by 0, that's indeterminate. So when you think of indeterminate, what you kind of should think is think of this as I need to do more work. So this doesn't mean the limit doesn't exist. It doesn't mean the limit does exist, it means you don't know and you need to do more simplification of some kind to figure out if it works. Does that make sense? Okay, so if you get 0 over 0, that's indeterminate. If you get infinity divided by infinity, that's indeterminate. If you get 0 times infinity, does that look familiar? That's like the example that we just wrote down, right? Okay, that's also indeterminate. If you have, so a couple other ones that we won't see for a while, but 1 to the infinity, let's see. Oh, infinity minus infinity. Let's see, what's another one? That's good enough for now. There's some other more obscure ones, but these are kind of the main ones that we see, especially in the very beginning. Okay, so just a little note just to make sure. So how do you see if it's indeterminate? You plug in the value. So if the limit as x approaches 2, let's say, you plug in 2. Limit as x approaches 0, you plug in 0. Okay. Okay, so now once we have that, then if it is indeterminate, wowzers. Okay, all right, so you're going to simplify and use the limit laws. Okay, all right, so let's do an example here. Let's say we have the limit as x approaches, how about 2? We'll do a simple one first. How about x squared minus 4x minus, or let's do plus 4. Let's see. Over x minus 2. Okay, so the first thing you do, you plug in the number. So I'm going to plug in 2. So let's see here. So if I plug in 2 here and 2 into all the x's there. So what do I get? Okay, 0 over 0. So I get 0 over 0. So what does that mean? Yeah, that means it's indeterminate. This means more work. Okay, now more work kind of depends on the kind of function you have, but here we have polynomials, so the first thing you kind of want to try is just to factor. So if you factor the top there, what does that factor into?
X minus 2 squared.
So this is x minus 2 times x minus 2 divided by x minus 2, right? Okay, now so we're not going to do this. Typically we'll skip this step, but I want to do it since this is the very beginning. I want to do it so that we can make sure that we're doing things properly. So what you do at this point is you use the limit laws to break this up. And so here, if I break this up into, say, x minus 2 over x minus 2 times the limit as x approaches 2 of, what would be that second limit?
X minus 2.
X minus 2, right? On top? Okay. All right, now, is this an appropriate use of the limit laws? Yes. Why? Why is this really different from the one that we had written down earlier where we said this is not okay? The difference is that what is this limit right here? The second one, this one. What is that? The limit as x approaches 2 of x minus 2. So x minus 2 is just a line, right? Is it continuous? Sure. So how do you evaluate a limit if the function is continuous?
Just put in the value.
Just plug it in, right? So you plug it in. Okay. So What do I get when I plug in 2? I get 2 minus 2, which is 0. Okay, fair enough. Now, what is this limit right here? Now that kind of looks like it doesn't exist, right? Because you have a 0. If you plug in 2, you get a 0 in the denominator, right? But what's the wrinkle? What allows me to actually break this up this way?
Is that equal 1?
It does equal to 1. Does it always equal to 1?
When x does not equal 2.
As long as x doesn't equal 2, right? But since we're evaluating the limit as x approaches 2, does x actually ever equal to 2? No. So that's the key right there. Is that so? This is equal to the number 1. That limit because x is never equal to 2. Does that make sense? So we use the limit laws to break it up, and that allows us to evaluate each one. Yeah? Now, typically, kind of what we'll do is we'll go back. So let me just kind of go back a step here. So like if I'm looking at this, probably your instinct is to kind of go like that, right? Yeah. You know, I mean, you've taken quite a few algebra classes in your day. And then if you do that, you end up with that, right? Which is equal to 0. So that's the same thing that we got when we did it the long way. And we typically will kind of jump, but I wanted to make sure that we knew why we were allowed to just cancel those out. Yeah? Does that make sense? Okay, so any questions with that? So I know that's a pretty easy example, but the main thing that I wanted to get across is this idea right here, together with the limit laws and why we're allowed to break that up into 2 limits.
So why is that not considered indeterminate?
Yeah.
The x minus 2 over x, x approaches 2.
Well, the difference is that at this one right here, if you plug in the number, so plugging in 2 is so that if the function is continuous, then you found the limit and you're done. Now, if I plug in 2 into the original, this one right here, I don't really know if the limit is actually going to exist or not based on plugging it in there. It's only after I simplify it a little bit that I'm able to see that that the limit will exist. So here, let me give you kind of contrast a couple of really sort of simple examples. Let's say you have the limit as x approaches, say, 0 of so on purpose I'm making this extra simple. Okay, so these are 2 different limits, right? So notice if I plug in 0 for both the first one and the second one, both are indeterminate, right? You get 0 over 0. Now at that point, when you plug in 0, do you know whether the limit exists or not? No. So indeterminate just means you don't know if the limit exists. It may exist, it may not exist, but you need to do some more stuff to try to figure it out. So you simplify it, and what do you get for this one? This is equal to, yeah, well, if you want to do kind of the, well, actually, I mean, yeah, so let's skip the simplification step for the extra step for now, but that's just the limit as x approaches 0 of x, right? Which is equal to what? 0. Now, what does this look like graphically, this one? Well, this looks like it's a line, right? And then there's a hole at 0. That's why the limit exists. Okay, but what about this one? This is the limit as x approaches 0 of 1 over x. What is that? It does not exist, right? So that's the thing, is that it could be one or the other. It could be that the limit exists and you just don't know what it is. You need to do some more work. Or it could be that the limit doesn't exist. But if I, for example, ask, well, what's the limit as x approaches 4 of the 1? What is that? Hint, it's easy on purpose.
Does not exist.
It's just 1, right? The limit as x approaches 4 of the number 1 is 1. Yes? You with me? It's easy on purpose. What does 1 look like? What's the graph of 1? It's a horizontal line, right? It's always equal to 1. Always, no matter what. So it's equal to 1. Okay. All right. Is that any different from that, for example? Isn't x plus 2 divided by x plus 2 equal to
1.
That's equal to 1, right? Okay. Unless x is negative 2, exactly. So you're right. It's equal to 1 unless x is negative 2 up here, right? But here I'm not interested for all x values. I'm actually only interested as I approach 4, right? So is this really any different from this? It's not really.
One.
It's, I mean, the function, well, the function that's on top and bottom are different, but all 3 of these, they're all equal to the number 1. You guys see why? Because they're all equal to 1 as long as the denominator is not equal to 0, right? Is the denominator ever equal to 0 in this one? No. Is the denominator ever equal to 0 in this one? No, right? Because you're taking the limit as x approaches 4, not equaling to 4. Now, why is it that sometimes we actually plug in the number? It's because of continuity, yeah. Because if it's continuous, the limit and the function have the same value. That's why it's a tool to help us evaluate the limits. Yeah?
So we can plug it in for sine functions and cosine functions?
Anything. You always try to plug it in, always. But you might have to do more stuff to figure out what the limit actually is. Yeah? Let's see. Okay, so what about... Okay, so let's do some more examples. Let's say you have the limit as x approaches, I don't know, let's say 25, x minus 25 over square root of x minus 5, let's say. Did we already do this one? No? Okay. All right. So what do you guys think about this? What do I do first? First thing, always. Plug it in, exactly. So I plug it in, and what do I get? 0 over 0, right? Okay, so what does that mean? More work, right? It's indeterminate, more work. So notice, is this factorable? At least not in the conventional way that we normally factor. It actually is a little bit factorable, but so you can do funny factoring. So there's actually 2 ways to do this problem. You can do funny factoring, or what do you typically do when you have radicals and you multiply by the conjugate, right? So like for example, you could do multiply by square root of x plus 5. And if you do that, let's see, what would you get? You would get the limit as x approaches 25. What would I get on the bottom? X minus 25, right? Okay. And what do you notice?
You can cancel the x minus 25.
Yep, can cancel those guys, right? So then what is this equal to? So now that you're left with only square root of x plus 5, plug in 25 into there, and what do you get? You get the square root of 25 plus 5, which is 10. Does that make sense? So that was different, right? So polynomial, you do one thing. Now you have radicals, you do something else. Another way, just to kind of give you another option here. If you look at x minus 25 and you kind of factor it forcibly into a difference of squares, what would it be?
Square root x, square root x 5, square root
Mhm. Looks like that, right? Do you guys agree that that works? That works out? So it isn't a type of factoring that you would do in your algebra class, for example. But it's convenient here because notice if I change, so if I have that, right, square root of x minus 5, so notice I didn't have to multiply by the conjugate, but they cancel out, right? Bless you. And then what do you end up with? Yeah, same exact thing, right? Yeah? Questions? That make sense? Okay. All right, I'm going to give you guys one to try. You ready? Try. Let's see. How about... let's see. Limit as x approaches. Pick a number. 15. Oh my goodness. Okay, let's do 7. Let's see here. How about 7? What is that? 2. Oh, I forgot. What's 49 times 7? 263? Is it?
343.
I totally blanked. I'm normally pretty good at this.
343.
49 times 7. 343. See? Terrible. Terrible. Don't tell anyone I did that. I'll lose all my math cred. Okay. All right. I'll give you guys a few minutes to try that one. A couple minutes, maybe. All right. So you guys ready? Let's do it together. Let's see what you guys got. So the top is a difference of cubes, right? So what would that look like? That would be x minus 7 times x squared plus 7x plus 49 divided by x minus 7, right? Okay, so then we simplify. And after we simplify, then what do we do? Yeah, plug in 7, right? Yep. Let's see. So what is that? How many? 147. That sounds about right. Easy, right?
Yeah.
Okay.
Why we can't write it as x minus 7 times x minus 7 times x minus 7? Why we can't do that?
Because it doesn't equal. Because if so that would mean that this right here would be x minus 7 times x minus 7. But is that true?
No.
It isn't, right? Because if you FOIL it out, you get x squared minus 14x plus 49, right? Which is completely different. So Any other questions with that one? No? What about the second one? What do you get when you plug in 1?
No, you get in.
So this is it's a little bit different, right? Because what's going on here? If x is approaching 1 from the negative direction, and I have 1 over x minus 1, what is that? Yeah, it's definitely going to infinity or minus infinity, right? Because you have 1 over, and then the bottom's getting really, really, really small, right? So we're going to look at limits that are going to infinity and negative infinity in more detail in a little bit. But like if you just kind of imagine, so the bottom, notice, is approaching 0, right? Does that make sense? It is approaching 0. So kind of think about the progression here. So like this is like, let's say 1 over 0.1, 0.01. What's happening to these numbers?
Getting smaller now.
Well, the bottom's getting smaller, but overall,
It's getting bigger.
it's getting bigger, right? So like this first one is 10, right? This is 100. This is 1,000. But and so the bottom keeps getting closer to 0, and then so the whole number gets bigger and bigger and bigger. Now this isn't quite right, because what's wrong with that? Yeah, then it's actually negative, right? These are all should be negative. Why? Because so if you think of numbers, if x is approaching 1 from the left, from the negative direction, what are the numbers that you're kind of thinking? Yeah, they're less than 1, right? So when I take a number less than 1, subtract 1, well, you're going to get a negative number, right? Does that make sense? Okay. So what's going on here? Well, this is going to minus infinity, right? You guys agree with that? This first fraction right here. This one. Yes? Okay. What about the second one? Is it negative infinity again? It's a little bit easier to see if you factor the bottom, I think. So if I factor this, you would get x times x minus 1, right? So if x is approaching 1, what's the sign of those numbers, of the x times x minus 1? It's going to be negative, right? Does that make sense? Why it's negative?
Yeah.
You sure?
Because the x minus 1 is always going to make it negative.
Right, this is negative. X minus 1 is negative. What is x? It's always going to be positive, right? Because x is approaching 1, positive 1. So then overall, the denominator is going to be negative, right? So then this is also approaching minus infinity, right?
Mm-hmm.
Okay. So what is that? Negative infinity plus infinity, exactly. Okay, so this is, because notice you're subtracting the minus. So negative infinity plus infinity. Well, what in the world's that? Is that 0?
Indeterminate?
Indeterminate. That's exactly right. Indeterminate. So if you go back here, let's see. Where is it? Right there, right? Infinity minus infinity. That is not equal to 0. It could be 0, but it's not guaranteed, right? So this is indeterminate. Okay. So what should I do? More work, right? Now, so here I have two fractions, so what's the natural thing to try? Find the common denominator, combine them into one fraction, and then simplify, right? Okay. All right, so let's try that. So let's go over here. So I have the limit as x approaches 1 from the left. Oh wait, x minus 1, right? And then x times x minus 1. Okay. All right, so what does that equal to? This is the limit as x approaches 1 of, so what's my common denominator?
X minus 1 times.
X times x minus 1, right? So here, this one I multiply by x, right? Top and bottom. You guys agree with that? So then what would that be? That would be x minus 1 on top, right? So now what?
Cancel.
Cancel. So what am I left with?
1 over x.
Okay, which is equal to what?
One.
1 over
1.
1, right? So be careful. So, just because there's like a minus there, don't think that it's going to be negative or something. So x is approaching 1, and the function 1 over x is a continuous at 1. It is, right? So if I take the function 1 over x, this is my function. What's f of 1?
1.
It's just 1, right? Is 1 over x, so it's a rational function. So a rational function is continuous on their domain, right? As long as it's not on the vertical asymptote, then it's continuous. So 1 is in the domain, so it's continuous, right? Yeah? So if the function's continuous, you just plug it in, you're done, right? No need to, finagle it around or do any shenanigans. That's all you need to do. Okay, so questions. Does the strategy make sense for kind of the overall strategy? So notice how it's a little bit different. You don't always do the same thing, but the kind of overall idea is always the same. Yeah? Yes?
In the previous example, you said that we could plug in, I think it was 2 because it never actually hit 2. Was that
You mean when I was doing this one?
yes. But in this one, we can just plug in 1 and that's fine. I'm kind of confused on that. I don't know if I'm making any sense, but
You are making sense.
is this like a different situation?
No. So I'm trying to think. Well, okay. So let's go back to this one. So let me just make up something else here. Let's say the limit as x approaches 4 of, I don't know, x plus 1. Okay. What is it that allows me to say that this is equal to 5? First of all, where did I get 5? I got it from plugging it in. What is it that allows me to simply plug in 4 into x plus 1 and get 5? Yeah. So the reason I can do that is because x plus 1 is a linear function, and linear functions are continuous. Okay. So that's what allows me to plug in. Okay. Now, what's the difference with that compared to this? Well, is this function continuous at 4?
No.
It is not continuous at 4. So can I plug in the number 4?
No.
No. Okay, good. But what do I also notice about this function? That as long as x is not equal to 4,
It'll continue.
It's continuous.
yes, but it's equal, specifically it's equal to the number 1, right? So in this case, I'm not actually plugging in the number 4 to get it, because it's not continuous at 4, so I can't plug it in. But x minus 4 divided by x minus 4 is always equal to the number 1, as long as x is not equal to 4, right? And so that's why. So it is different, and I think maybe that's what was causing confusion. Yeah. Any other questions? No? Okay. Then why don't we take a little break, and then we'll come back and we'll start talking about limits with infinity. Kind of contrast that. So let's see. How about 6:40? Sound good?
Wednesday? All right.